Good afternoon, everyone. Welcome to the second session of our Introduction to Quantum Computing workshop series. Yesterday, we sent an information email to our participants about next week's sessions, and also Canvas system invitations were sent in a separate email. So please check both your inbox and spam folders. In the session, Dr. Türkmenci will talk about postulates of quantum mechanics, Bloch sphere representation, tensor products, multi-qubit states, multi-qubit quantum algorithms, entanglement, and quantum teleportation. Before give the floor to Dr. Türkmenci, I have a quick question for him. Would you prefer me to interrupt the presentation with questions, or do you prefer to answer the questions at the end of the session?
Yeah, no problem. You can interrupt anytime.
Okay, thank you. Thank you so much. So, floor is yours.
Okay, I shared my screen. If it's available, I will continue. All right, welcome everyone again. I'll continue with day 2. In the previous lecture, we made a very fair introduction to the mathematics of quantum computation. And we will continue from the postulates of quantum mechanics again, the basic assumptions of quantum mechanics. The second postulate is about the time evolution of a quantum system. Here it is. The time evolution of a closed quantum system is described by a unitary transformation. In fact, we talked about the unitary operators in the previous lecture, and we had a small expression about that. We had an implication that unitary transformations are deeply related with time evolutions of quantum systems. Here, explicitly, we can see that. Assume that we have an initial state psi when we have an initial when the time is 0, which means that this is an initial quantum state. And when we apply a unitary gate to that, we obtain the quantum state at a later time. Okay, so this is that simple. But here we should underline that the postulate 2 applies for closed quantum systems. And in fact, the Schrödinger equation applies for closed quantum systems, which means that the system is assumed to be not interacting with the outer universe. Okay. So an alternative version of the second postulate about time evolution is that the time evolution of a closed quantum system is described by Schrödinger equation. So Schrödinger equation, time-dependent Schrödinger equation, is a linear differential equation. And here we see, again, the psi. And here we see an operator H. And we will call this operator as Hamiltonian, which is related with the energy of the quantum system, in fact. But for now, let's assume it as just an Hermitian operator, okay? So we know the properties of Hermitian operators, again, by the previous lecture. So if we solve this linear differential equation, what we are going to find, the first version of the postulate, psi t is equal to a unitary operator multiplied by the initial quantum state, okay? Here, e to the power minus I ht is a unitary operator, and we see that it is an exponential operator, okay? Here again, the operator h comes into play, and again, this is the Hamiltonian. But in general, in quantum computation, we do not deal with time and the Hamiltonian structure of the Hamiltonian because this is more physical. But still, I would like to introduce the Hamiltonians in this lecture very slightly, even it is a physical quantity, because I would like to make you understand the deep insight of the unitary operators because they are performed by Hamiltonians, and I would like to see their time dependence. Let's have a quick look at the Hamiltonians. What are these operators in quantum mechanics? So the observables are described by operators in quantum mechanics, which in turn to be represented by Hermitian matrices. Okay? So the Hamiltonian is the observable corresponding to the total energy of the system, and its eigenvalues are the total energy of the system. And we know that the eigenvalues of Hermitian operators are real. So energy should be a real quantity. Okay. Now consider an electron spin or just 1 qubit quantum system, the simplest possible quantum system that we can see. Such a quantum system can have, for example, a spin Hamiltonian. In the previous lecture, we talked about the spin operators. So this is a spin operators SZ, and this is omega. So this omega is going to be attributed with frequency. We can talk about frequencies more deeply. For example, Larmor frequency in the magnetic field, making a spin precession. But these frequencies can be varied from one platform to another platform. And here we are talking platform independent. So this is just a single qubit Hamiltonian. Here, what we see is a sigma Z Pauli gate. So these gates, these Pauli operators that we have seen in the previous lecture, we understand that they are deeply related with the Hamiltonians. Okay. So this is a single qubit quantum system Hamiltonian. Okay. And we keep that in mind, and we directly jump into the representation, visual representation of a qubit state. So we can visualize a qubit state in terms of a sphere geometry, which we call a blob sphere. So this is a blob sphere representation of a qubit. So in the previous lecture, we considered a qubit as a two-level quantum system, just like this, alpha multiplied by 0 plus, for example, beta multiplied by 1. So these are the computational basis states. And this is a two-level quantum system, okay? And these alpha and beta are unknown coefficients that we want to learn at the end of the computation. And here we see that in the blob sphere representation, in the poles, we have the basis states. We have our basis states, okay? So in general, we talk that these basis states are orthogonal. So in Euclidean geometry, we know that the orthogonal vectors should have 90 degrees angle between them. But when we map the two-level quantum state into the Euclidean space, we see that this is not the case. So we have 180 degrees angle between them, but they are still orthogonal. So the reason and the proof of this is irrelevant in this lecture, but it has a mathematical explanation, of course, can be explained by group theory, but it's not our concern for now, okay? And on the equator, of the sphere, we see that there are superposition states. And here we see that we have a vector here. So this vector is the psi vector, which represents the quantum system, okay? And in the blob sphere representation of a qubit, the qubit is going to be represented by the parameters of this sphere. So what are these parameters? These parameters are expressed by some angles. So this theta angle is the angle between the vector and this axis. And this phi angle, which is a polar angle, is a vector between the projection of the vector, projection line of the vector with the plus axis, okay? So by these explanations, we can see that this two-level quantum system, can be written in terms of vectors and in terms of angles in this sense. So cosine theta divided by 2 multiplied by the 0 base states plus sine and 1 base states. Here we have also this phi angle. In fact, this is small phi, but it's implying the same phi angle here. So this is the phase vector, phase angle, I'm sorry, between the computational bases. Okay. So you can verify quickly that if theta is 0, then this term is going to vanish, and which means that when theta is 0, this vector is now sticked on this pole. So it's pointing the north pole of the Bloch sphere. Okay. So you can extend the examples, and if you put theta an angle, you will see that theta can be on this plane. And if you also vary the value of this phi, you can rotate this vector in this plane. So these rotations are all corresponding to the unitary operations. Okay. So we will conclude and we will say that these rotations correspond to some operators. We are going to see this now. So rotations on the Bloch sphere. The rotations on the Bloch sphere are unitary operations, and they preserve norm because the length of the vector will not change during these rotations. And in fact, all these unitary operations, one-qubit unitary operations, corresponds some operations, okay? But they are unitary operations. Let's make an example. Find the unitary gate performing an X rotation with theta angle, okay? Just like this. If you want to rotate this initial vector or our state in an initial state 0, so this is the x-axis, and if you rotate this just like this, and this vector will be in this final state. This initial vector will become this final state with angle theta. Okay, how can it be possible? Please find the unitary gate performing this X rotation with angle theta. Okay, let's try to find it. First, we should understand that all rotations in the Bloch sphere can be achieved by Hamiltonians. Okay, so the X rotation can be achieved by an hx Hamiltonian with a corresponding time t. Okay, so this hx rotation Hamiltonian can be written in terms of omega sx, and the inside sx, we know that this is 1 divided by 2 multiplied by sigma x, where sigma x is the polar x operator. Here, if you multiply this with t, because we have this in the formula, we have an omega t here, and this omega is a frequency which has a unit inverse time, and time has the unit time, of course, and when we multiply this, we will have a dimensions quantity, which we call the radian angle, okay? This theta is equal to omega t. So therefore, the rotation operator will become to this exponential form, okay? So sigma x is still a matrix represented by 2 by 2 dimension. So this is an exponential matrix problem. This becomes to an exponential matrix problem, but this is in fact the answer of my question. So this is the rotation which is needed to make an X rotation in my block sphere, but I can expand this expression. I know that I can expand any exponential function in terms of Taylor expansion. And if I do the same for this problem, and if I make a simplification by taking theta divided by 2 as theta prime, my problem becomes, by using this expansion, Taylor expansion, into this form. And if I carefully make some algebraic calculations, I can see that the even this is also something that I know. The even powers of Pauli operators corresponds to the identity operator. So we know that what's an identity operator? An identity operator for any dimension is equal to 1, 1, and 0. Off diagonals are 0, and the diagonals are 1. So this is an identity operator. For larger dimensions, of course, the diagonal entries are always 1, and the off-diagonal entries are always 0. So this is an identity operator matrix representation. And the even powers, the odd powers of sigma x, in fact, the odd powers of all Pauli operators correspond to that operator itself. So if we know this, and if we continue the expression just like this, I can write this expression in this way, okay? So clearly I can see that my expression becomes this expression, and this is in fact the series expansion of cosine, and this is the series expansion of sine trigonometric term. So writing this terms here in detail, so I can find a new expression for my rotation operator. So clearly, this is a unit operator again, and this is my Pauli X operator. And if I want to express this final result in terms of matrix presentations, I can clearly write in this way. So if I drop these coefficients inside the matrices, and I will obtain this rotation operator in terms of matrices, okay? So I can repeat all these results in terms of other rotation operators, and we can generalize this for all rotation operators. And here is my rotation operators in terms of matrices, okay? And you can also find the matrix representations of these rotation operators. So these are just 1 qubit rotations in a single block sphere representation, okay? But we should assume that, or we should express that this rotation, but in which direction, or in which counterclockwise or clockwise operations, the always counterclockwise rotations are assumed to be positive, and the clockwise operations or the rotations are assumed to be a negative rotation. Okay, so this is the way how we assume these rotations. Okay, we should have some remark. Assume that we have an arbitrary single qubit unitary operator, and any operator can be written in this form. So this is a phase factor, and this is a rotation operator. This means that in the previous lecture, we have seen single qubit operations. So this can be an Hadamard gate, or this can be any other quantum gate, say U. So this means that this U can be written in terms of rotation operators in the block sphere. So why is it important? Because in normal computers, in classic computers, when you press a button on your keyboard, so it is compiled into zeros or ones into machine language. So this is something we already know from our classic information. In quantum computer, when you press a button or when you send a comment to the computer, all these commands are translated into unitary rotations, which can be expressed by block sphere rotations. So this is important for quantum compilation. So this is the quantum compiler, okay? Let's go on from here. So we also have some exercises, okay? And you can prove that if you multiply the Hadamard operator, just like sandwich, between X, Y, and Z, you can obtain these identities, okay? Why are they important? They are important for making some circuit simplifications. When you write circuits, you will need some identities. Okay, you can prove them very easily if you are fond of multiplying small dimensional matrices. Okay, and the next postulate, this is about the measurement. Okay, the measurement is not a straightforward thing in quantum mechanics. Quantum measurements are described by a collection of measurement operators, and these operators acting on the state space of the system being measured. Okay. So here the M index refers to the measurement outcomes that might occur in the experiment. So this is my postulate. Okay. So if the state of the quantum system is, say, psi before the measurement, then the probability that the result M occurs can be found by this inner product. Okay, this is the way how I obtain the probability of measuring the system in a specific quantum state. So, and the system after the measurement becomes in this collapsed state. Okay, my state can be in a superposition state, which is a linear combination of lots of bases. But after your measurement, the final state is going to be just one of them. Okay, so this is what we call the collapse of the quantum system. After that operation, the system will be always measured in that specific system. So this is the final state that we obtain. Okay, so let's see it with an example, but before, we should be able to understand some properties of the measurement operator. Again, each measurement operator is Hermitian, which means that when you multiply these measurement operators by themselves, you should obtain these measurement operators again. And they should obey the completeness relation. If your dimension is 2, you should have 2 measurement operators, okay? And if you add these measurement operators by this multiplication rule, you should have the identity operator. Okay, these are 2 important properties for these measurement operators, or simply projection operators. Okay, now let's try to see this. Measure a qubit in computational basis by using the facts in postulate 3. Okay, again, we are just measuring a qubit. It's just a 2-level quantum system. Okay, so this is a measurement on a single qubit with 2 outcomes defined by the 2 measurement operators. So here, my 2 measurement operators, M0 and M1, are described by this outer product form, 0 outer product 0 and 1 outer product 1. So from the previous lecture information of us, we already know that this outer product, because we know that outer products are always operators, this is equal to this matrix representation, and this outer product is equal to this matrix representation. Okay, if you add them, if you add them, what you will obtain is, of course, an identity operator, okay, as it should be, because of the completeness relation requirement. Yes, they are again measurement operators. And another property, does it satisfy the another property? Because this is the measurement operator, and I know that the square of this measurement operator should be equal to itself. If you multiply it by itself, what you will find here is going to be, I'm sorry. So this is an inner product, and it could equal to 1, and what you obtain the measurement operator itself. Okay, they satisfy, and they are really my measurement operators in two-level complex Hilbert space. So these are my cubic measurement operators or projection operators. Now, suppose that the state being measured is this. So this is a usual qubit state, okay? And of course, let us try to find the probability to find the qubit in state 0. If you want to find the probability to find if you want to find the probability to observe the qubit in state 0, you should use M0 measurement operator here. And the way you apply this measurement operator is just like this. So if you take this inner product, you will find the probability, find the qubit in 0 states after the measurement, okay? And of course, similarly, this probability of obtaining the measurement outcome 1 is here going to be B modulus square, and the probability for measurement outcome 0 is going to be A modulus square, okay? And the state after the measurement in two cases is going to be in this form, A divided by A modulus multiplied by 0, and B divided by B modulus multiplied by 1, 2. Okay. So simply how it is possible, we can also check this, because here we implicitly assume that this multiplication is equal to this, okay? Is it really the case? Of course, this is the case, because I have A0 plus B1 here. And in front of this qubit state, I should put this measurement operator. And if I multiply this measurement operator with this summation, this is just a complex coefficient, so I can write this A in front of this term, and what I will obtain is 0 outer product. So this term with this term, and this term plus B, again 0 outer product, and this term. So this is simply 1 because of the identity, or they are the same states. And this is, of course, 0 because of the orthogonality. And what I will obtain this term, okay? This term is the result of my multiplication, and it should be divided by this, okay? Yes, this is the case, what I will obtain after the measurements, okay? But here, I would like to stress one last thing about these measurements. Assume that I have a complex number. In general, a complex number can be defined by a real part and a complex part. Here, this e to the power I phi is called the phase of the complex number, okay? So now assume that we have two states, psi described by this qubit state, and psi multiplied by a phase factor. So in fact, this phase factor is in front of the global parenthesis. Okay, so we will call this phase as a global phase. Okay, so this is just like this. Okay, parenthesis, and out of this parenthesis, this is multiplied by 8 to the 5. Okay, this phi is not here, so it is in front of the global parenthesis. So therefore, I call this as a global phase. So my question is if this phase is observable or not after the measurement. Okay, so if I write this here, so this becomes just as usual by linearity. I can write it in front of each basis state. But what happens in the measurement? What is the probability to find the state after a measurement? So by the measurement probability rule, I should write these states just like this, because if you want to write this just like this, you have to multiply it forward, right? And if you take a dual, because of the probability, because of the properties of the Hermitian conjugate, if you want to write this state in this dual form, this coefficient will have a minus form, and you should write it here. These numbers are these numbers are not operators, so they will cancel each other because you can write them anywhere. So this means that this is just equal to the usual formula, which means that I can ignore these phases. Okay. So the global phase is not observable. The global phase is not observable by a measurement. It doesn't matter. It's not important for us. Okay. However, if there is a phase, not as a global phase, but somehow, if you are capable to write or to register a phase in front of just one of the basis states, this is called a relative phase. And this relative phase is observable after the measurement. For example, these two states, these two superposition states are differing by a relative phase, because here this I to the I phi, e to the I phi is equal to 1, and here it is equal to -1. So these two states are completely different states, and they behave differently after the measurement. So finally, we can say that global phases have no observable measurement result. Therefore, relative phases contain reliable quantum information. Okay. Now let's come to the final postulate of quantum mechanics that will help us to understand the multi-qubit states. So postulate 4 is about the composite systems, which are necessary to understand the multi-particle systems. The state space of a composite physical system is a tensor product of the state spaces of the component physical systems. Moreover, if we have systems numbered from 1 through n, the joint state of the total system is represented by the tensor product of each individual states, starting from psi1 to psi n. So here, this multiplication with a circle is not a matrix multiplication, normal matrix, or it's not an operation multiplication. It is called a tensor product or direct product. So it has different matrix multiplication properties, and we will talk about that. So if we have a 2-qubit quantum system, just like this, we will denote the tensor product operation by this symbol, and we will write the whole system, Hamiltonian, for example, by H1 tensor product H2. So H1 and H2 corresponds to the individual Hamiltonians of the system. So what about the dimensions? What about the dimensions? So we know that if you are multiplying two matrices, the dimensions of these matrices should obey some rules. But in tensor product, these rules do not apply. Okay, so if here I can have both two-level quantum system or multi-level quantum systems. It doesn't matter. But if my dimensions are n1 and n2, I will see that these matrix the tensor product matrix multiplication rule is different. Now, let H1 and H2 be two Hilbert spaces for two qubits, and I can describe the basis by the whole system, to describe the whole system by this tensor product multiplication. Okay, let me take again the example in terms of qubits. Okay, if we have a two-qubit system, my basis states for two qubits, my all basis states for two qubits are going to be written in terms of these tensor product multiplications. Okay, I can have 0, 0, 0, 1, 1, 0, and 1, 1 basis states if I have two qubits. Okay, so this means that for a single qubit, my basis states are 0 or 1. But if I have a system consisting of two qubits, now this is my system, but inside the system I have two qubits. Now to describe the system mathematically, my basis states are 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So of course, this notation is the same with this notation, and this notation is also the same with this notation. Okay. They all imply a tensor product, or this one. These are all implying two-qubit systems. So order is very important here. So this is the first qubit and this is the second. Okay, or here, the first qubit, the second. First qubit and the second. Okay. Okay, this is the basis state representation if I have more than one qubit inside my whole system. Let's proceed from here. Okay, next, the effects of the operators to these multi-qubit states. Okay, now let A, operator A, is an operator that acts on vectors phi, which is belonging to the first system, defined by the first Hilbert space, and let B, an operator that acts on vectors defined by T, which is belonging to the second Hilbert space or the second system. Okay. So we can write an operator A multiplied by B that acts on vectors phi and T as follows. So this is the right way to multiply operators on these operations. Okay. Here, operator A is acting on this space and operator B is acting on this space. Why? Because this is the first order and this is the second order. And this is the first order state and this is the second order state. This is the first order operation and this is the second order operation. All operators only act on their own space. because this matrix dimension matches with this matrix dimension, and this matrix dimension may match with this matrix dimension, okay? But what happens if I want to, this just like this. This is my first system, and this is my second system. So A can only act on this system, and B can only act on this system mathematically, okay? But if you want to act B to this system, then you should write in this way, B tensor product A. So B tensor product A multiplied by phi and key. Then B will act on this, and A will act on this space, okay? And another question can come easily here. And what happens if I want to only act A to the first state, and if I want to act the state B nothing, okay? We will see it in the following slide, but before that, this is the same thing with A acting on A and B acting on key, okay? It's just the same thing that we have followed. Now let's try to understand how I can tensor product two matrices, or what is the mathematical equivalent of the tensor product. So tensor product means here, if you want to tensor product A with B and say A and B are both 2 by 2 matrices, this means that you are multiplying the first element of the first matrix by the all elements of the second matrix. This A11 is being multiplied by B completely. And of course, this A12 is being multiplied by the all elements of the second. So after the multiplication, what you obtain is the following, okay? So this is the side. So this corresponds to this. A11 is multiplied by B11, B12, B22, and B21. So which is, in fact, this second matrix. And this part belongs to this part, okay? And so on. So I have a larger matrix that I expect. Why do I have a larger matrix? Because I have 2-qubit system. So my dimension should be larger, and the state space should be larger. And this is the operator that acts on the state space should also be larger. And it should match, the dimensions should match with them, okay? So this is the tensor product matrix multiplication representation, okay? So let's see this with a simple example. Now, these are the X and Pauli Z matrices that we have seen in the previous lecture. Let's tensor product X with Z. So this is the result. X and Z are 2 by 2 matrices, and if I tensor product them, what I will obtain is going to be a 4 by 4 matrix. If we try to write or represent the matrices, basis states for 2 qubits, this is the same multiplication holds to represent the basis states. 0, 0 state is in fact matrix multiplication, stands for that. Okay, so this is 1, 0, 0. If I have more qubits, of course, this multiplication will be extended. So I have 4 by 4 matrix as an operator. And of course, this operator should match with this state. 1, 0, 0, and 0. Okay, so you can multiply these matrices, or this operator x multiplied by z can be applied to this state 0, 0, because the dimensions match. Okay, and likewise you can find the other basis state matrix representations. It's straightforward to find. This is 0, 0, this is 0, 1, this is 1, 0, and this is 1, 1. Okay, if I have more, then the dimensions will be more. Okay, now here, for tensor product, how to compute inner products? If I have two states with multiple in a subspace, just like this, let's inner product psi1 and psi2. Okay, what is the rule to inner product then? I know what an inner product is by the first lecture. So this is the way how I inner product psi1 and psi2. If you want to inner product them, this is the notation what you do. And the result is, of course, again, a C number. But here, psi1 is the first order and T1 is in the second order. Therefore, if you want to inner product, this psi1 should be inner product by psi2, because this is the first order and this is the first order. And you should inner product T1 with T2, and because this is second order state and this is the second order. So this will be inner product with phi1, and this is the inner product with chi1 and chi2. So this is the this is the way how we can inner product of multi-qubit states. So let's see more properties about the tensor products. The tensor product of two vectors is linear, which means that I can write or distribute this tensor product over summation in this way, or in the other order. And moreover, the tensor product is linear with respect to scalars. If you have a scalar number in front of the second space, this scalar number can be written in front of the whole space. So in fact, this is a very important property, because if you don't want to measure this one, this state, or this qubit, if you want to sacrifice this qubit by measuring, you can find out this alpha valuable information by just making measurement to this qubit. So this is an important property for us. Okay, if you want to apply an operator A on the first space, the way we apply is the following. Okay, we want to apply A to the first space. So mathematically, how to construct the relevant operator? You should apply, or you should tensor product with the identity. Why do we have an identity in the second order? Because I don't want to apply the single qubit operation to the second qubit. Okay, so this is the way how you act this single qubit operation to the first qubit. Of course, if you want to apply it to the second qubit, then this order is going to be changed. So this is a multi-qubit quantum circuit, for example. So in the first lecture, we have seen single qubit circuits just like this, but I can have multi-qubit states just like this. Here, this A qubit is acted on the first qubit, and this B, for example, is acted on the second qubit. Or alternatively, an operation or an operator can act to both qubits simultaneously, not a local operation. So the C operation can be acting on the two qubits at the same time. We will call them as two-qubit gates or multi-qubit gates. Up to now, we have just seen single-qubit operations. Okay? But the way to represent these circuits is to tensor product all these gates. So this A, B, C operations acting on these qubits are represented by the tensor product of these qubits. Okay? But if we have an operator acting on just some of the qubits, not all the qubits, again, to write the matrix representation of this, you will just write the matrix representation of U, and here there will be nothing. So you should write the identity operator. So this identity operator, of course, should be the dimension of this identity operator is up to how many qubits are there. Okay. If you have just like here 2 qubits, then this can be represented by here there is nothing, here there is nothing, and identity operator multiplied by identity operator. Of course, this is 2 by 2 identity operator multiplied by U. This is acting on 2 qubits. So this is a 4 by 4 matrix. And here again, I have nothing. 2 by 2 identity operator and 2 by 2 identity operator. So this is the matrix representation of this block. Okay, because I apply this quantum circuits as blocks by blocks. Okay, so this is the block that represents A, B, C, and this is the block that represents only U. Okay. So this is the way how I calculate the dimensions. Here, if you want a break, we can give a 10 minutes break, or if you want to go on, we can go on. I don't know, in the first lecture, I guess someone asks for some break. You can write on the chat. Shall we go on or have a break? Okay, then I will continue. Okay. So let's conclude by 2-qubit quantum gates. Here we talk about single-qubit quantum gates, and now we are ready to talk about 2-qubit quantum gates because we have seen the tensor products. The most elementary and significant quantum gate is a controlled, not or controlled operations. So a CNOT gate or controlled NOT gate is a 2-qubit quantum gate, which applies a NOT operation to a target qubit depending on the state of the control qubit. So the circuit symbol of a CNOT gate is in the following here. So this means this qubit is a control qubit. Let's call it qubit A. CNOT A means this A qubit controls the target qubit. So this qubit is a target qubit. Okay. And it applies in the following manner. So this is the first qubit, and this is the second. Okay. The rule is in the following. If the first qubit is in the state 0, apply nothing to the control, apply nothing to the target qubit. So starting from 0, 0, my result is again 0, 0 state. Okay. if my initial state is 0, 1, still my control qubit is 0. So the final state is the same. But if my control qubit is 1, apply NOT gate to the target. Then my final state is 1, 1. And here, my initial state is 1, 1. The control qubit is again 1. And if I apply NOT gate to the target qubit, my second qubit state will be inverted, and what I will obtain 1, 0. So this is the logic under this operation, okay? And in fact, this is the truth table of C0 gate. So this operation, so this is just the effect of initial and target state, but still we don't know something about the matrix representation of this gate. Here is the matrix representation of this gate. Okay, so if I write here, you can also apply it. So this is 0, 0. It maps 0, 0. So this is 0, 1. So this is 1, 0. So this is 1, 1. 0, 1. 1, 0, and 1, 1. So it maps 0, 0 to 0, 0. So I have 1. It maps 0, 1 to 0, 1. It maps 1, 0 to 1, 1. So therefore, I have 1 here. And I have 1, 1 to 1, 0. I have another 1. So this is the reason why I have such a matrix representation. So, but be careful, this part of the 4 by 4 matrix is directly looking as a NOT gate. Okay? And we will also decompose this representation and find the Dirac representation of this gate. But what happens if my control qubit is the second qubit? Say qubit B, if this is the control qubit, this is my circuit representation, and I will always see such circuit representations. Of course, I can write how the result is going to be in different notations. In these notations, this is addition in the modulo 2. And A and B always takes values 0 and 1. You can check the results here. Just like C0 A, C0 B can be applied like this. And the rule is now, if the second qubit is in state 1, then apply NOT gate to the first qubit. And if you apply this truth table, and this is the circuit, this is the matrix representation of C0 gate with a different target and control qubit. Okay, the controlled operations can be generalized to any unitary operator U, which means that two control operations are not, of course, necessary control NOT gates. Any controlled operation can be applied for any unitary single qubit gate. Then, if the control qubit is 1, you apply this U operation to the initial state. And what you obtain is this 4 by 4 matrix representation. Okay. Here, I would like to give you the Dirac notation representation, because here in the previous slides, I show you that this was 1, 1. I have here 0, 0, 0, 0, 0, 0, and NOT gate. Let me write without writing these zeros. So this is the C0 gate, okay? And in fact, this is equal to this 0, 0 plus 0, 0, 1, 1. So if you can decompose this C0 gate just like this, or any U gate just like this, in fact, you can write this. Okay, this is a 4x4 matrix, and in fact, this matrix can be written in this form. Okay, this is the tensor product of these two matrices. You can verify if you tensor product this with this, what you will obtain such a matrix. Okay, but you know what this matrix is. This is zero out product, 0, and this is the identity matrix. Therefore, I can decompose this control operation just like this, plus this one. Because this is also the matrix multiplication by this. So this is in fact NOT gate, and this is 1, 1 outer product operator. So instead of a NOT gate, there can be any gate here, this one. So the general structure is in this form. So this is the Dirac notation representation of a controlled operation, and this is the matrix representation of a controlled operation. Okay, let me clear the board, and the compositions are going to be so significant when constructing the circuits. Okay. And I have another important representation. If I have an open node controlled gate, the rules are just slightly different. It is as follows. If I have 0 on the control gate, then apply U operation to the target state. If I have 1 in the control qubit, then apply nothing to the target. So this is the open node rule for the control U operation. So this is the matrix representation. As you see here, these open nodes are also significant for some reason. But for now, you will just have to learn this. Another 2-qubit gate, important 2-qubit gate, is swap gate. So it just exchanges the bases. Swap gate operation is just swaps the qubit states. If you have 0, 0, of course, they are the same. There will be nothing. If you have a 0, 1 initial state, it swaps with 1, 0. If you have 1, 0, it swaps with 0, 1. If you have 1, 1, of course, they are the same. So this is the matrix representation. And I need these kind of swap gates very much because of lots of reasons. Okay, and a question for circuit representation. Okay, if I have such a circuit, prove that they are identical. A control you get with an open node control is equal to a closed loop control multiplied by X gates on the first qubit. So again, we can solve this proof identity first by reminding the control U gate Dirac representation. This was a Dirac representation. Likewise, the control U gate with open node control can be represented by this Dirac representation. Now, I will try to prove that this is equal to this. Okay, how can I do this? So I will just use a simple trick because I know that this 0 is equal to x1. What was x? X is the NOT gate. So if you apply NOT gate to 1, what you will obtain is 0. Then I can simply write here that if I write here x on the right and on the left, please remember that x is an Hermitian operator, and I can write x just like this, because in fact I should write this dagger here, but I don't need that dagger because they are equal. It is completely equal to 1, 1. Okay, so instead of this, I can write this. Okay, now I will follow the same route. Okay, and instead of the 0, 0, I will write the following on the left. I will write 1, 1, x, x, and instead of this 1, 1, I will write x, 0, and x, 0. So they are the same thing, okay? They are the same. But after this, I will make another trick. Now I have a global parenthesis here. I will take this x and this x on the right of the parenthesis, okay? But I cannot write simply x, because this x is in the first order. So what I should write is the following. I should write x tensor product 1 here. And for this x, and this x, I will write to the left-hand side of the parenthesis. And if I do all these things, what is left inside the parenthesis is the following. So what is left inside the parenthesis is simply the controlled U operation. Okay. So starting from here, I have left here, or I have left here, okay? But up to 2 x gates on the left and on the right, and you see that these x gates have been written in the first order, which means that they are being acted on the first qubits from the left and from the right. So this circuit is equivalent to this circuit. So you can write circuit identities, or you can prove circuit identities in this way. So this is one of the ways. Okay. Okay. Next, of course, I can have more than control 2-qubit gates. So this is, assume that this is a control U gate. Okay, this is a control U gate, and this U gate can be applied to more than 1 qubit. So assume that this is a U gate, and this is a control U gate. And this control U gate can be controlled NOT gate. Okay, then I have, my dimensions are larger. You can if you want to, if you love to multiply the matrices, you can see that these identities are holding. Or you can decompose a single swap gate into 3 CNOT gates in different orders. They are all circuit identities. And in fact, we have more circuit identities, but these circuit identities is not of our interest for now, but you can prove yourself. Another important property is called phase kickback phenomenon. And this phenomenon is very useful for more complicated algorithms, which is known as phase estimation. But we will not see that. The phase kickback is a phenomenon which is very useful for eigenvalue problems. So what is an eigenvalue problem? Please remember from the linear algebra course, if you have a matrix or if you have an operator acting on a vector, if you have such an identity, an operator times a vector equal to lambda times the same vector. So this is an eigenvalue problem, and this lambda is an eigenvalue. Okay, so we can have the same equality in quantum computation, just like in this manner. If I have U operation acting on a quantum state, and if you have a lambda in front of this, so this is again an eigenvalue problem, and this lambda is an eigenvalue. In this state, satisfying this equation is called an eigenstate. Okay? So in general, this lambda is in this form. E to the power 2 pi phi. Okay? And in general, this phi is in modulo 2 numbers, 0, 1, 1, 0, 0. Starting from 0 because the integer part will make no sense because it will be a global phase. So this was to remind the eigenvalue problem. Assume that we have such a circuit, and this is a control U operation, and assume that this state is an eigenstate of U. So only in this case we can talk about this. And here I have a plus state. We know that this plus state in fact means this plus state is in fact this superposition state plus 1. Okay. And here, this is my initial state. This is my initial state, U. Okay, this is the plus state and this is U. And of course, I can distribute this U from this order. What I will obtain this. Here, there is the control operation, which means that if the first qubit is in state 1, apply the U operation. Okay. So this in this distributed summation, in this part, the first qubit state is 0. Therefore, I apply nothing to this U. But in this part, the first qubit is in state 1. Therefore, I apply U to the second qubit, this qubit. And I know that since this U is in the eigenstate of operator U, after this implementation, I have a lambda factor in front of this U coming because of this eigenvalue problem. So this factor, this number is in front of the second qubit. But because of the tensor product properties, this factor can be written in front of this first qubit. And if I take again U to the global parenthesis, what I obtain is the following. Now I have this factor as a relative phase factor on the first qubit. So this is still the first qubit. This is still the first qubit. Here I have a tensor product, and this is the second qubit. This means that by this operation, a phase factor is being extracted, and this phase factor information is sent to the first qubit, which means that this information, by measuring this first qubit, you can probe this information from the second qubit. And you can still continue making or implementing unitary gaze to this qubit because you didn't implement any measurement operator. But here you have implemented a measurement operator to this qubit. You cannot use that qubit anymore because the state has been collapsed. But you have taken information from the second qubit without collapsing the second qubit. So this phenomenon is called phase kickback. And because of this kicking this phase in front of this first qubit, you can take information from the first qubit, which is belonging to the second. Okay. These are all some important properties of controlled operations and the tensor products. And now we are ready to learn something about quantum entanglement. Why? Because we know multi-particle states, multi-qubit states, and the strange entanglement phenomenon. Now we are ready to understand this. But surprisingly, we will see that it has a very simple mathematical explanation. A quantum state phi is said to be separable if it can be written in a tensor product form of two distinct quantum states. Phi is written in terms of tensor product of phi1 and phi2. If you can write this, so this is a separable state, and a separable state is not entangled, okay? Second, if these substates of phi cannot be written in a tensor product form, then this state is entangled. So this is that easy. If you cannot write in terms of this tensor product states, then phi is an entangled state. Let's try to understand in the very simple form. For example, this superposition state, I'm omitting the normalization condition here. 0, 0 plus 0, 1 is not an entangled state because it can be written in this form. You can take this 0 into the global parenthesis here, which means that this is the first qubit and this is the second qubit, and these two qubit states can be written in a separable manner. Then this state is not an entangled state. However, these states that I write, these four states that I write under this example, these four states are entangled states because you cannot write these states in a tensor product form. Try, you will not be able to write, okay? These are special four states in two qubit form, which are called Bell states. In fact, they are also called maximally entangled states up to some reason, okay? Or EPR states, okay? So these are entangled states, and B00, B01, B10, and B11. So these subscripts, in fact, denote how they are produced initially, okay? So this is the simplest circuit identity or circuit representation to obtain these qubit gates. If you want to create, for example, this 0, 0 plus 1, 1 state, you need a Hadamard gate following by a CNOT gate. So, for example, if these initial states, instead of X and Y, if you write 0, 0, and if you write here the Hadamard gate and this control NOT gate, okay, what you will obtain, for example, my initial state is 0, 0. If I write this in the Hadamard gate, now, again, I'm omitting the normalization condition. Hadamard gate to the first qubit, which I write in this manner. This Hadamard gate is being active only in the first qubit. And here, my second qubit state, okay? So my first qubit became this superposition state after Hadamard gate, okay? And I can also write this in this form because this 0 can be expanded just like this, 0, 0 plus 1, 0. And the following gate is the C0 gate. You know how to implement C0 gate now, okay? Please tell me the initial qubit here. If initial qubit here is in the state 0, I will apply nothing to the second qubit. And if the initial qubit is 1, I will apply the target qubit, not gate. So my final state is 0, 0 plus 1, 1. Okay. So this means that this beta 0, 0 mean. So for this reason, I write here beta 0, 0. This has been obtained by the initial state 0, 0. Okay. If my initial states were different, you could obtain different types of Bell states. Okay. 0, 0, 1, 0, which has been written in the previous slide. Okay. This was the simplest case to obtain the Bell states. In fact, this simple circuit is called a Bell state generator. And from these initial states, I obtain 4 different Bell states, just like the following. And you can do it yourself. It would be a nice and simple exercise for you. And next, extremely important another theorem, which is called no cloning theorem. Okay, copy paste possible. The no cloning. What does it mean? Can quantum information be copied or not? Now we are trying to understand this. Suppose we have a copying machine with initial state psi s, and assume that I have a unitary operation acting both of the qubits, and at the end of this unitary operation, my initial state psi is copied on this S state. Okay, so this is a copying. Is that possible or not in quantum information theory? So this is my question. Okay, so this is in fact the same thing. I have a unitary operation U, and it affects this copying procedure here. So what I see from this algorithm, I have PCS initially here, and this U operation is acted on this initial state. And after this implementation, I obtain this final state. So I have psi, the first qubit has been copied or has been overwritten on this second qubit. So is that unitary operation possible or not? So we'll just try to understand this by using the inner product property of tensor product. Suppose this copying procedure works for 2 particular pure space, phi and psi, okay? Then we should have the same for this, okay? U acting on this initial state, and I have psi, or U acting on this phi S state, and I should obtain phi. Okay. Now assume that I inner product these 2 equations from the left. For example, take the Hermitian conjugate of the first equation and multiply the result with the second equation from the left. So what would I have? What should I have? Okay. So if you take the Hermitian conjugate of this equation, both sides, what you will obtain is psi and S and U bigger. And this is equal to psi and psi. That should be. And if you multiply this with this equation, what you should obtain is the following. U, phi, and S. And of course, the second part, phi and phi. Okay. So simply, this is identity. I don't have anything here. And of course, because of the multiplication rule of the inner product, this should be multiplied by this, and this should be multiplied by this. So what I obtain is phi inner product multiplied by this. So phi, psi phi, and psi phi. Here I have psi phi 2 times. So I have this square, and I have this the same on the left. So this is just like x equal to x squared. Okay. So what is the solution of this equation? The solution of this equation is x equals 0 or x equals 1. Okay. What does it mean? What does it mean? Or what did I find? Let's try to understand this. But first, I want to erase all these things because I have already found this. What I have after all these operations is this solution. What does it mean? What does it mean? This means that this inner product can be 0 or can be 1. It cannot be another thing. Okay, I don't have another solution. If this inner product is 0, this means that I have an orthogonal state. And if this is equal to 1, this means that they are the same quantum states. They have the same overlap. First, I don't want to copy the same. I don't want to copy the same quantum state because this is already the copy. Okay, so this is something that I don't want. The only choice that I left is this orthogonal state. But if 2 quantum states are orthogonal, so this is not very interesting because it looks like it is a classic state. So this means that 2 quantum states can only be copied if they are orthogonal. But orthogonal states are all already the classic states, and I already know that the classical information can be copied. So I conclude a general result, a general quantum cloning device is impossible. I cannot clone or I cannot copy an unknown quantum state by this simple proof. Okay. And finally, let's implement a circuit which is known as a quantum teleportation circuit. Copy-paste is not possible, or a general procedure for copy-paste is not possible, but cut-paste possible. Is it possible if I could send an unknown quantum state at a distance? So, in fact, it is proven to be possible. We call this as quantum teleportation. Just like in the famous movies, this is not the same procedure in the famous movies because we are just sending an information or teleporting a quantum information to a distinct place, okay? So assume that initially we have 3 qubits and assume that 2 of these 3 qubits are initially entangled, okay? So this is my initial assumption to send or to teleport a single qubit information. Here we have 2 parties, Alice and Bob, who are the standard people in quantum information. Alice has 2 qubits in herself, in her side, okay? But the second qubit of her is initially somehow entangled with Bob. And Bob has only 1 single qubit. Okay? So we have an algorithm here to implement this teleportation. Here, we want to teleport an unknown quantum state just like this, initially alpha and beta, which means that I don't know alpha and beta in advance. And here is my quantum teleportation algorithm, okay? And here, this is my initial state that I would like to teleport, okay? And here at the end of the algorithm, I want to obtain this psi here in the third qubit. These are very single operations, but here there is going to be some local and classical operations also needed to complete this procedure. Here I have some lines, timelines or state lines to follow step by step. And this is a very instructive example. Here you see that I have the first qubit, which is belonging to Alice. The second qubit is also belonging to Alice, but the second qubit is initially entangled with this third qubit belonging to Bob. So my initial state is psi and beta 00, an entangled state. And this psi is alpha 0 plus beta 1. And if I multiply it with this entangled state, what I will obtain is this state. Okay. So this is a zero node. After multiplying this unknown state by 0, 0, you will obtain this state. You can obtain it very easily because I have written that the first qubit state was alpha 0 plus beta 1 multiplied by this beta 0, 0. So this is 1 square root 2 0, 0 plus 1, 1. Okay, yeah, we write this factor at the very beginning of these terms, in front of these terms. And this alpha is again in front of the first term. And I multiply this with this, in fact. And what I will obtain are the 4 terms, in fact, but I didn't manage to make this multiplication. Just I want to multiply this alpha and beta, okay? What from here I obtained here, okay? And then what I see here, I have a C-NOT gate here. Okay, I have a C-NOT gate. Again, remember the rule of C-NOT gate. If the initial state of the first qubit is 0, the target qubit is the second qubit. Apply nothing to the second qubit. And if the initial state is 1, apply the NOT gate to the second qubit. So here, the difference from here to here should be in these terms. Here, this is the second qubit because it is in the second order. 0 has been flipped to 1, and 1 has been flipped to 0, just like here. And this is after this operation, I arrive with psi 1 here. Okay. And next, I have an Hadamard gate applied only on the first qubit. And this is our first qubit state. And this first qubit is going to be 1 square root plus 1 when you apply this Hadamard gate here. And also this gate or this state is going to be in this form 1 square root 0 minus 1. Okay. And after that, if you disturb all the terms and after some algebra, in fact, this can be a little boring, but you have to do that. You will arrive these equations. Okay. You will arrive psi 2. Here, now we are here and ready to implement these local measurement operators. So in fact, Alice is applying these M1 and 2 measurement operators on her qubits. Now we have a huge superposition state, and these first 2 qubits are in pure states, and the final 3rd qubit is in a superposition state. It's resembling the initial psi qubit that we want to send. But after these operations, the system will collapse one of the eigenstates. But which of them? We don't know, because the quantum measurement is probabilistic. Therefore, Alice is now applying some measurements. And after this measurement, the first 2 qubits will be in 0, 0, or in 0, 1, or 1, 0, or 1, 1. If the measurement result of first 2 qubits is 0, 0, this means that the 3rd qubit is in this state. Or if the measurement result of first 2 qubits are in 1, 1 state, this means that the 3rd qubit is in this state. But Alice cannot force her qubits to collapse to the desired state. What she can do is to send her results to Alice by telephone or by any classical communication channel. So this is called classical communication, assisted quantum teleportation. Here, classical communication is necessary. Here, to complete the teleportation, Alice has to perform measurement on her qubits and send the information to Bob, which state the system has been collapsed. Okay? If the result is 0, 0, Bob should do nothing because should perform an identity operation because his qubit is already in the state that we set. Okay? If the measurement result is 0, 1, then this one, then Bob knows that he has to perform X gate on his qubit because if he apply the X operation, he will recover the initial state alpha 0 and beta 1 because X operation will flip this quantum state into the initial quantum state and so on. So this protocol means these X and Z or these Bob, these are the measurements that, or the operations that Bob performed depending on the measurement results of Alice. And after all these operations, now teleportation is complete. Okay. Okay, and finally, this was all for our course, two-day course. And I would like to advise you some resources. Here, the usual book of quantum computation written by Nielsen and Chuang, just like the holy book of quantum computation. And I have another special offer to you by David McMahon. This is the book with worked examples. And this is a good book for you to make your own exercises. And finally, you can find some online resources, okay, from YouTube, or there are lots of online channels. I hope you enjoyed the 2 days course, and I'm here if you have some questions.
And I would like to say thank you to our instructor, Dr. Türkmen, for all the information that covers and explains all the fundamental concepts very well. And also, I would like to thank him once again for his time and valuable contribution. Our workshop series will continue with the Kubernetes training on December 18th. As I mentioned at the beginning of the session, we sent a detailed email about next week's Kubernetes training yesterday. And also keywords, Canvas learning system invitations were sent in a separate email. Please check both your inbox and spam folders. If you have any questions, contact us via email or Discord channel. And if you have questions for the session, we are here for a couple of minutes. Maybe I should stop the recording.